Good evening, students. We already discussed two postulates. This is the postulate number 3. In third postulate, we have to discuss about the every observable OBSCR, every observable in classical mechanics, observable every observable in classical mechanics is represented by a linear Hermitian operator, by a linear Hermitian HERMITI Hermitian operator in quantum mechanics. That means every observable in classical mechanics. That means what you observe in day-to-day life, or what you observe in whatever happening surrounding you, can be represented by a linear Hermitian operator in quantum mechanics. Suppose I tell that if I observe that, suppose I tell that this is a road. Suppose I observe that this is a man. Suppose I observe that this man starts moving towards this direction. Suppose I observe that this man starts from here and reaches here. That means some distance he covered. That I observe in classical. That means this is my observation that initially when I start to observe this person, he stand in this position. After 5 minutes, I saw that he starts walking, and I observed that he reaches here. That means he covers some distance, 2 meter, 3 meter, or something else. He tells that whatever we observe in day-to-day life, that means here I observe that this person will move from one place to another place. That can be represented by a linear Hermitian operator in quantum mechanics. Remember, Hermitian starts from capital H because it is a scientist name, mathematicians. So any researchers or any scientist name should be starts from capital, wherever it may be. Okay. Suppose I tell that, any name, I consider the classical mechanics symbol. Classical mechanics symbol. In classical mechanics, how we make a symbol? Quantum mechanics symbol. Quantum mechanics symbol. Then what is operation? Okay, suppose I tell that first is position. Here in this position is here initially. After 5 minutes, I saw that it starts walking and it is here. This is the final position. In classical mechanics, we represent it as x, distance covered by x. In quantum mechanics, I represented it like s cap. Then what is the operation? Now multiply by x. Multiply by x. This is the operation. That means whatever you, suppose I tell that x is equal to 1, 3x. That means if we consider that x is equal to centimeter, 1 centimeter, so he covered 3 centimeter, but covered 3 kilometer, but covered 3 meter. Okay, if x is 1 meter, okay, position. Similarly, if this is in case of linear cases, oh, suppose in case of radius, suppose in case of circular path, what we do? Now radius r. In quantum mechanics, I write r cap. And what is the operation? Now multiply by r. Multiply by r. Similarly, momentum. We can represent in classical mechanics px. In quantum mechanics, px cap. And what is the operation? Now minus is bar dou by dou x. Okay. Similarly, kinetic energy. Classical mechanics symbol is kx. Quantum mechanics symbol is kx cap, which is becomes minus h bar square by 2m dou rho square by dou x rho square. Potential energy Pe. Classical mechanics symbol Vx in x direction. Quantum mechanics symbol Vx cap multiply by Vx. Total energy. Here total energy I write E, but quantum mechanics we write H cap. Total energy means kinetic energy plus potential energy is total energy. So kinetic energy minus h bar square 2m dou rho square by dou s square kinetic energy plus potential energy, which is called as the total energy. Then angular momentum. We can write it classical mechanics Lx. Here we can write Lx cap. Here we can write what is the operation? Minus is bar bracket y dou by dou z minus z dou by dou y. Suppose you write Ly in y direction. It is y. Then we can write minus is bar. We take here Ly, Lxy minus is bar. Here we write z dou by dou x minus x dou by dou z. Similarly, if you take Lz, here Lz cap minus is bar x dou by dou y minus y dou by dou x. Whatever you take that direction, we do not take in these cases. Suppose x here, we take yz. If you take y here, y direction, we take zx. If you take z direction, we take xy. Okay, in this way you can find out any type of. Then what is the Hermitian operator? I tell you, let the operator alpha cap is said to be Hermitian. If it satisfies the following condition. If it satisfies current one. If it satisfies the following condition. Then what is the condition? Now minus infinity to plus infinity. We can write alpha cap psi I asterisk psi j dx should be equal to minus infinity to plus infinity psi I asterisk alpha cap psi j dx. That means if minus infinity plus infinity alpha cap psi I asterisk psi j dx, if we find out this value on the left hand side and we find out this value in the right hand side, minus infinity plus infinity psi I asterisk alpha cap psi j dx, if both right hand side and left hand side is equal, then we tell that this operator alpha cap is Hermitian operator. Here asterisk means the complex conjugate. If any imaginary value is there, then we put minus sign, otherwise not, it will remain as such. Okay, that means if the left hand side, we find out this value left hand side, whatever the value we get, and if we find out the right hand side, if the right hand side value is same, that means left hand side is equal to right hand side, then we tell that the operator alpha cap is said to be Hermitian operator. Then how to take a operator? Suppose we know that kinetic energy, how we convert? You see here half mv square, that we know, the kinetic energy. If what we do, now we multiply m divide m. Multiply m divide m, no problem. 1 by 2m divided by m, multiply by m means m square, v square. Then we can write kx 1 by 2m mv whole square. This is nothing but momentum, p is equal to mv. So what? The kx 1 by 2m px, suppose I consider here x, px square, p is equal to mv. Then if we convert px is a classical mechanics, if we convert them into quantum mechanics, ps cap, if px is substituted by px cap, then kx, this kx is converted to kx cap. How? Now we see here, suppose kx we get 1 by 2m, we have to substitute px with px cap square, okay, which is equal kx 1 by 2m px, I substitute this value, minus is bar dou by dou x square, minus minus plus, so kx 1 by 2m, here minus minus plus, so we get here I square, h bar square, dou square by dou x square. Then what is the value? Kx is equal to I square means minus 1, imaginary number minus, I write here 1 by 2m h bar square dou square by dou x square. It is nothing but this one is equal to kx cap. Here you see minus h bar square by 2m minus 1 into h bar square minus minus h bar square by 2m dou square by dou square by dou square. Here you see the simple kx is converted to quantum mechanical operator. Okay, this is how you convert a classical mechanics symbol into quantum mechanical operator. Okay, this is the result that kinetic energy calculated based on classical mechanics gives the consequence of kinetic energy operator. That means whatever we observe in classical mechanics, we can convert it into quantum mechanics. Okay, this is what the postulate number 3 tells. Then what about the postulate number 4? Any measurement of the observable, any measurement of the observable any measurement of the observable associated with the operator alpha cap associated with the operator with with the operator alpha cap with the operator alpha cap will yield the result as eigenvalues. Eigenvalues an of the corresponding operator. Of the corresponding operator which satisfy the following eigenvalue equation. We satisfy the eigenvalue equation. That means alpha cap psi n is equal to an psi n. That means here psi n is the wave function by any function. Alpha cap is the operator. If this operator operates this function and we get the same function, but there is a coefficient. That means any operator which operates a function, any function, if we get the same function in the result along with coefficients, then we call that function is the eigenfunction, and the equation is called eigenequation, and an, the coefficient, is called as the eigenvalue. Okay, that means this is the operator, any operator which operates this function, we get again the same function. Psi n, we also get psi n. This is called eigenfunction, and this an is called eigenvalue. Okay, it's called the eigenvalue, and this is called eigenvalue equation. Okay, similarly, if we apply the Schrodinger equation h cap psi n, what we get? Na e psi n. Here same function we get. This is the operator. This operates this function, and again we get the same function along with coefficients. So this function is called as eigenfunction, and this E is called as the eigenvalue. That means the psi n is called Ein function. E is called Ein value. So this equation is called Ein value equation. Okay, suppose I tell you that if a operator dou by dou x, it operates e to the power ax. What we get? Now a, again we get e to the power ax. This operator operates this function e to the power ax. We get again this function and this value. This is a is called Ein value. Because this function operates this operator operates this function, and we get again the same function with some value coefficients, and this is called Ein value. This is called Ein function. Okay, this is what we call postulate number 4. So postulate number 4 tells you that any measurement of the observable associated with operator alpha cap will yield the result of Ein value. We get Ein value n of the corresponding operator. Corresponding operator is alpha cap, which satisfy this Ein value equation. Okay, this is called Ein value equation. Then postulate number 5. If a system is in a state, if a system is in a state, if a system is in a state is represented by a normalized wave function, by a normalized wave function, psi, then the average value average value basically written like this. This is, if we write this symbol, we will know that this is average value of the observable corresponding to the operator corresponding to the operator alpha cap is given by below. If a system is in a state represented by a normalized wave function, this wave function is normalized. That means psi integration of minus infinity to plus infinity psi asterisk dx by d tau is equal to 1. Normalized wave function. Then the average value basically written like this, average value of A. That means this one of the observable corresponding to the operator alpha cap केंता में लिख परबा हमें एंता करिकी greater than less than. This is means average. How we get this average value? Minus infinity to plus infinity. We get psi x asterisk alpha cap psi x dx. This is, if we, in order to get the average value, we have to take whatever the function you take, wave function, we take complex conjugate of the wave function, then the operator, and which operates the wave function psi x. This operator will operate this wave function, not this wave function. This operator will always in front, not back. This operator will operate this wave function. Then whatever the result we get, again you integrate, with multiply with this one, then integrate with respect to dx. Suppose I take one example. Suppose I write that alpha cap psi nx is equal to an psi nx. Substituting this in equation 1, this equation alpha cap psi nx, if we put this in this equation, if we put this one with this equation, we get, this is the average integration minus infinity to plus infinity. Here wave function is psi nx. This is asterisk, then alpha cap, then psi nx. Okay, dx. Then what we do? Psi alpha cap psi nx is equal to this one. So in place of this or this, we put this one. Integration psi n janta achi santa. In this place, I write this value. An psi nx dx. This is constant, comes outside. An minus infinity to plus infinity psi nx asterisk psi nx dx. This is nothing but this one. We know that. We know that minus infinity to plus infinity psi asterisk psi dx is equal to 1. Normalized equation. So this is nothing but 1. That means an, this one is equal to 1. Normalize. So which the answer is an. So we get this one. So average value is equal to an. Okay, so this postulate is also called mean value theorem. This postulates is sometimes called mean value theorem. पढ़ा थी वह तुम्हारा? ओहो, mean value theorem. This postulate is also called as mean value theorem. So, if we write example average value, x, I consider x. What is the average value? This is the average value of the position x of any system. How we can write? Average value of the position of any system. You can write here any system means any movement, any particle movement, any system, any system you consider, particle movement, man movement, human being movement, whatever. What is the average? Suppose I start from Bhubaneswar, comes to the Baleswar. If I cover the distance 200 kilometers, then if anyone asked me what is the matlab, what, how many times it required to reach to Baleswar, I tell that 4 hours. Then what is the average velocity of a vehicle should be? Now 200 kilometer divided by 4, we get 50 kilometer per hour. That means a bus will move 50 kilometer per hour. Sometimes it may be 60, sometimes it may be 100, sometimes it may be 10. But when you take average 100, 60, 10, 20, if you take average, it will comes around 50 kilometer per hour. Velocity. Similarly, what is the average distance? Matlab, I can write that minus infinity to plus infinity psi asterisk psi dx. If we find this value, if we find this value of any operator is position, so we write here position. If we write here position, that means if s cap, similarly, if we take the average value of x square, then what should be my equation should be? Now my equation, how to find out average value? Now minus infinity to plus infinity psi asterisk x square cap psi dx. So any such type equation we can write. Suppose what is the average momentum? Px minus infinity to plus infinity psi, suppose x is written here, psi x asterisk px cap psi x dx. The matlab minus infinity to plus infinity psi x asterisk, in place of px I can write minus I square dou by dou x psi x dx, because px is written like this. Anything else you can write. So the probability, the wave function psi should be normalized. So the important application of the mean value theorem lies in the calculation of uncertainty. The uncertainty in position and uncertainty in time, or Heisenberg's uncertainty principle. You know, the uncertainty in the position and momentum of a particle, using the relation how to find out uncertainty, delta x uncertainty in position is equal to how we calculate x square. That means this one, if we find out this value, I write this one minus x the square to the power half. Half matlab square root. Similarly, uncertainty in momentum px square average value minus px the whole square to the power half. We get uncertainty. हमें लिखना कहते ना 3 plus minus 0.1. This is uncertainty. How this value will come? Now this value will come from these two calculations. if it is position or it is momentum. So anything else we can write, position, momentum or any other value. So this is this uncertainty 0.1 calculated from this equation or from this equation. Okay, this is all about postulate number 5. I will end here because time, the data will be more.